Hello, it's been a while. Um, I'm going to record a video explaining what is a quantum computer and how does it impact the current cryptography that is in use. So this is the high-level agenda. We're going to be discussing about basics of current cryptography system and what is a quantum computer, how does it impact the current cryptography, and what is HNDL. Anytime you hear the words quantum computers in with respect to the computers, or internet, you'll always hear this term HNDL, harvest now, decrypt later. So we're going to talk a little bit about what exactly that means or that threat is. And then I'll end with a short demo of HNDL. Um, that's about it. So to start with, so how the current cryptography works. So in current cryptography, there are two type of, uh, in cryptography, there are two type of encryptions. It's symmetric encryption and asymmetric encryption. Symmetric encryption means we use the same shared secret key to encrypt the data and decrypt the data. So let's say there are two different sites, site A and site B, and you're sending a traffic from site A and to site B. You don't want to send it over the public internet in a clear text manner. So you want to encrypt it on site A using one shared secret key. Let's say the key is secret. And when you receive the same data on site B, you use the same shared secret key, which is secret, to decrypt the data. Now, the biggest challenge is how do we derive the same shared or agree upon the same shared secret key between the two sides? That's not easy, right? You might think, okay, IPsec, you can configure shared secret key. Well, but when it comes to TLS, the user is unknown. So there is no predefined shared secret key between you and the website that you're trying to access. And that's where we use asymmetric encryption, where we have a pair of keys, typically called public and private key pair. And whatever you encrypt using one key, the other key can decrypt, but only the other key can decrypt, not any other key. So those two keys are mathematically linked to each other so that if you encrypt something using a private key, you can only decrypt using the associated public key and vice versa. So how is asymmetric encryption helps us with symmetric encryption? In two ways. One, to authenticate. So when you want to communicate or access a website, you want to make sure you're accessing the legitimate website. How can we assure that, or how can we ensure that? So that is based on the certificate that we currently use. So the website that you're trying to access, it will send its certificate, which is signed by the CA's private key, which can be decrypted using the CA's public key. So again, if you see, you're signing with the private key, and anyone having the public key can verify that message. So that's how you verify the certificate. And similarly, in you can use it for encryption also. Like you are sending the public key out of the internet, and anybody can encrypt a message using the public key, which can be only decrypted by you, who is holding the relevant private key, or yeah, relevant private key. So that's the high-level introduction about symmetric and asymmetric encryption. So we use something called hybrid encryption, where we use the asymmetric encryption for key derivation, shared secret key derivation between the two devices, and to authenticate the peer. And once it's authenticated, and once we are settled with the shared secret key, we switch to symmetric encryption using either AES or ChaCha20, which are the commonly used encryption algorithms now. So we use symmetric encryption because it's much efficient, CPU friendly, and it's much faster. You can't do asymmetric encryption for actual data traffic, which is practically it's going to consume a lot of CPU cycles. Okay, a little bit of introduction about this asymmetric encryption. It's the foundation of asymmetric encryption is, let's take two numbers, for example, 61 and 53, and we are keeping that as a private number or private key. And you simply multiply them and you derive the number 3233. You are sending that 3233 publicly from site A to site B. Anybody in the internet can see, but The fundamental reality is just by having the public key 3233, nobody will be able to derive that 61 or and 53. That's what we used initially to derive the 3233. Well, by looking at this number, you might say it's very easy, like I can do it on my head. But in reality, we use, for example, the one in the middle, 2048 bits, which is 617 digit decimal. Even the most powerful computer that we have right now cannot factorize such a big number. It will take millions of years to factorize if you just sit down and start factorizing one number, one uh, key. By the time we would have changed the key, right? So that's where it's secure. Now we use this concept in Diffie-Hellman, key exchange, RSA, key exchange or certificate or ECDS, H or ECDS. It's not the same multiplication. It's logarithmic algorithm on DH and elliptic-curve discrete logarithm on ECDH. But the underlying concept is still same. They are mathematically linked, and by having the public key alone, nobody can find the equivalent private key. That's the foundation of current cryptography or asymmetric cryptography. Now, switching gears to quantum computers. What is a quantum computer and how is it different than the current computer that we have, the modern computer, you can say? The modern computer or the computers um, deals with something called bit. You might have seen kilobytes, kilobits of data, right? So bit is nothing but it can either be 0 or 1. That's it. So let's say a equal to 0, you do the mathematical operations. And then if you want to do another mathematical operation, you have to change the a to 1 and do the second operation. Whereas when it comes to quantum computer, they deal with something called as qubit. And a qubit can be either 0 or 1 or both at the same time. That's the power. That's the power of quantum computer or qubit, actually. We're not going to talk more about how exactly this happens. It's a very interesting topic if you want to read about it. So there is something called um, um, wave particle duality of quantum particles, where um, um, I mean, an electron can be both wave and a particle at the same time. That's called superposition. And then there is interference concept in quantum computer. So there's a lot of interesting concepts in quantum computer, which is a little bit of outside of the scope of this discussion. I will probably record another video with um, what is a quantum computer in detail and what are the interesting things about quantum computer. But for now, all you have to understand is a qubit can be both 0 and 1 at the same time with certain probability of either 0 or 1 when you measure it. That's the one liner you have to understand to know about quantum computer for now. So how this quantum computer helps in mathematical operations? So quantum computer is not something like it's a super fast computer which can do everything very fast, whatever the current computer do. No, that's not the case. So quantum computers are designed to perform certain mathematical operations more efficiently. So if you take this as an example where there is a mathematical function to add two numbers, a simple function. So zero. So when you give a as 0 and b as 0, the result is 0. Similarly, 1 and 1, the result is 2. So you need four different iterations to evaluate all the possible outcomes of these two bits. Right? That's the current computer. It takes four iterations to come to check all the four possibilities. Whereas when it comes to a quantum computer, and a sub, if you have a quantum computer with two bits, and you can perform the four operations in a single go, just one go, it can evaluate or compute all the four operations and give you the results. So why is it dangerous? If you think about the previous example where we have this big number, and to derive the factors of this big number, it's going to take a lot of millions of years for current computer because it has to do the operations linearly, one at a time. Whereas a quantum computer with, for example, 2000 bits or more, it can perform these operations more efficiently and very fast. That's the biggest advantage of quantum computer, and that's why the world is investing a lot to to create quantum computer. Now, if it's so easy to do that, why don't we have? Do we already have a quantum computer now? We do. Then why the current cryptography system is not broken yet? Well, I wouldn't say it's not yet broken because nobody knows. Nobody knows if anybody even has a powerful quantum computer right now. All we know is if you have a sufficiently powerful quantum computer, the entire internet trust can be broken. The trust can be broken by forging the certificates, and the shared secret key that we are deriving between the two devices will no longer be a secret because anybody who has access to the public key, if they can derive the private key, there's no secret. So what are the challenges in developing a quantum computer? So the biggest problem for them is as they increase the number of qubits on a system, the error rate also increases. So they are struggling to increase the number of qubits, but at the same time, there are a lot of work and researches happening, as you can see by Google, IBM, Microsoft, every industry leader are doing a lot of investments and researches on quantum computers. So it's just one aha moment or one new discovery to scale the quantum computer uh, to a bigger size. And once they do that, the current internet is will be broken, completely shattered. You can read more about this later. I'm not going to go through all of them one by one. So, so now when it comes to quantum computer, and if you have a quantum computer, there is an algorithm, quantum algorithm, created by Shor back in 1990s. That time, nobody thought that algorithm will be used to factor the large number. But now that we are advancing more in quantum computers with the Shor's algorithm, it can just break the asymmetric cryptography completely. If you have a sufficiently powerful quantum computer, the RSA, DSA, Diffie-Hellman, ECDH, everything can be just broken. That's it. What about the symmetric key encryption, like AES and ChaCha, where we use symmetric key, shared secret key, between the two devices? That is still cannot be broken, even though there is a Grover's algorithm, which can increase the speed of trying to break the symmetric key, but it only reduces the strength. For example, if you are using AES 256 with a quantum computer, the strength reduces to AES 128 bits. It is still pretty powerful, not that bad, but it's recommended to use AES 256 because if you use AES 128, you are down to AES 56, right? So 64? Yeah, 64. All right. So again, the takeaway from here is with the quantum computer's arrival, all the asymmetric encryptions, everything will be at risk. Symmetric encryption is still safe with a reduced strength, right? So what is this harvest now and decrypt later? So let's say somebody captures the data between you and your bank or between two sites, the IPsec traffic or your TLS traffic. They can store it for years and years. They don't have to have a quantum computer today. They can just store it for years and years. And when the cryptographically relevant quantum computer arrives, they can decrypt the data. So are you okay in sending some data over the internet, knowing that somebody might decrypt it in the future? It depends on how critical your data is for you. So with that, let's take a quick demo of this HNDL, how exactly it happens. So I have a Python script which can, uh, okay, I have a Python script where you can enter the private key and decrypt or derive all the shared secret key used in the communication. So for example, I have I'll start with this. So I have this IPsec capture taken between two devices where you can see IKSA init, and then ICAUT, and then all ESP packets. So in IKSA init, so there is a key exchange data. This is the public key that I was referring to, exchanged between the two devices. So similarly, you can see a public key sent from the site, the device 2 to device 1. So using a quantum computer, the theory is using the private key, you can, or if you have a powerful quantum computer, you can derive the private key. So the moment I derive the private key, which means I can impersonate device 1. So if somebody can see, the only differentiating factor between the actual sender and somebody, a man in the middle, is the man in the middle doesn't know the private key. But if somebody can derive the private key, the man in the middle is no longer a man in the middle. He is actually a, a person who can impersonate you in the whole key exchange. How does it happen? So I have derived the private key of this public key. Don't ask me whether I have a quantum computer now. I don't have it now, but I have a way of finding the private key when the key generation happens on the device. So with that, I'm going to run my Python script where I'm going to enter my the private key which I derived, and I'm going to input the pcap, with the name hdl.pcap, hdl.pcap. Cool. So what happened now? So if you see in the pcap, the packet number 3 is encrypted, packet number 4 is encrypted. So these two are encrypted using the shared secret key we derived using the Diffie-Hellman key exchange that we did in packet number 1 and 2. And I already have the private key. So which means what exactly happened here? So we were able to successfully derive the shared secret key. And using that, we were able to derive all the keying materials that will be used to encrypt packet number 3 and 4, which means I should be able to decrypt packet number 3 and 4. I can see the proposals, the algorithm that is used, everything you can see. So the entire packet number 3 and 4, oh, even a certificate also you can see. So the entire packet number 3 and 4, you can easily decrypt because we already have the shared secret key derived. Now, we will do further key derivations for ESP. And again, as we can clearly see what is there in packet number 3 and 4, again, we can derive the relevant shared secret key. And with that help, we can see the entire ESP packets are completely decrypted. So I'll open this output pcap, decrypted, open, decrypted ESP. There you go. So what is there in the ESP? It's a sync and then there is a HTTP post with, oh, the username allies and password is secret. Interesting. So you see the thread, right? So you might ask me a question like, what if I use perfect forwarding secrecy where I do another Diffie-Hellman key exchange inside the encrypted channel? I don't care because I already have the initial keys. So whatever keys you are going to derive in the encrypted channel, it's all going to be inside. I mean, it's all going to be in clear text inside the encrypted channel. You already have your shared secret key for the encrypted channel. So that's the threat. So with this, do you think you are comfortable to use the current cryptographic system, or do you think it's the time for you to switch to PQC? That will be the next topic. What is PQC, post-quantum cryptography, and how can we protect ourselves from this threat to the current cryptography world? Thank you.